So let's look at chapter 31. So let's start with that. So basic idea is that a circuit is a closed loop. And we can say an electrical circuit will have a few electrical components, or we can say we'll have certain electrical components. And we can list a few of those components. Okay, so list of components. For example, so these are the components. We have one, resistors, or a resistor, and I'll list the component and its symbol. So resistors will have the following symbol like that, and then we can have a switch. Typically, a switch will look something like that. Let's say we have a capacitor. Capacitors will be represented as parallel lines that are equal that way. We can have a battery. Like that. So I draw it in that way so that you can see the difference between a capacitor and a battery. So for the capacitor, the two plates there are the same length as you can see there. Just make sure that they are the same length. We can have inductors also. So the inductor will look something like that. It's basically a coil. And then if we have a light bulb in a circuit, we can go this way. For a bulb, we can go like this. Something like that. Let's see other components. I think those are the main ones for now. We'll add to it as we go along. So let's look at 31.2, Kirchhoff's laws and basic circuit. So when we are ready to look at or analyze the circuit, the things that we need to know are the potential difference across each component in the circuit, and then we'll look at the current through each component. So that's where we'll start. So we'll say in order to analyze a circuit, we need to know one, the potential drop or difference. Potential difference is also called potential drop. Circuit elements are the same as circuit components, and then we'll need to know the current flowing through each element of the circuit. So to learn or to know those things, we need to use the junction rule and the loop rule. So we can say we shall use the junction rule and loop rules, or loop rule, to analyze a circuit. Okay. So first of all, we have the junction rule, which tells us that the current flowing to a junction is equal to the current leaving the junction. Okay, so we can say that current into a junction is equal to current leaving junction. Okay. So we wrote that last time as the sum of currents in is equal to the sum of currents out. Okay. So if we have a circuit, well, this is not a circuit, but let's say we have a junction like that. So this is current I, then this can be I1, and this will be I2. So we can say that the current in is equal to I, current out is equal to I1 plus I2, assuming that we have those two joining up like that. So this is the current in, and the current out is I1 plus I2. Well, let me do it this way. It should work out in the end. Just hold on. And so by the junction rule, or you can say by junction rule, so this is in, this is out. So you can say by junction rule, current in equals current out means I equals I1 plus I2. Okay, so that is the way we shall approach this. Okay. All right. And then we can look also next at the loop rule. So the loop rule just tells us that the sum of all potential drops in the loop is equal to 0. So sum of all potential drops or differences so suppose we have a loop, I'll show you in a minute. Suppose we have elements like this in a loop, like that. So this element has potential drop 1, potential drop 2, potential drop 3. So this is a loop. So we can say that since we are saying that there's a loop rule which says that the sum of all potential drops is equal to 0, we can say delta V1 plus delta V2 plus delta V3 should be equal to 0. Okay, so this is our loop. Okay, and those delta V's are the potential drops across each element in the loop. Okay, like that. So this rule was summarized to say that the sum of all potential drops across the elements I in the loop is equal to 0. So if you have 10 elements, you just sum them all up. So that's the loop rule. Okay. So we'll use this loop rule whenever we analyze a circuit, and there are a few rules of thumb that we can follow, which we will look at next. Yes. Okay. Hold on a second. This way. Yeah. Okay. So we can say that a few rules to follow when analyzing a circuit. Okay, so first of all, when we draw a circuit, we can assign the direction of current flow in any way we want. Okay, so first of all, draw and label the circuit. Draw and label. And then number two, assign a direction to the current. And in this case, we don't need to know what the direction of the actual current is. We just assign an arbitrary direction. If our direction happens to be opposite to the true direction, we just have a negative current. So it doesn't matter which direction you assign. Okay. And then we can say that if current is negative or is found to be negative, then we know that the current direction we assigned is opposite to the true direction. So that is the only penalty we have to pay for assigning the current in an arbitrary direction. If your current turns out to be positive after you calculate it, it means that you chose the right direction. If your current is negative, it means your direction is opposite to the direction you chose. So then you just make it positive. So it doesn't really matter. You know what it is in the end. So then, so now let's go on. So number three. Travel, you go around the loop, so travel around the loop. Okay, so the way this works is that if you go from negative to positive, so one, if you have a battery like that, if you are going this way, this is negative, that is positive, then the potential difference or the EMF of the battery, hold on a second. So in this case, the potential difference of the battery is equal to E, or positive. Okay, this is positive. Number two, let's say we have, let me redraw this. So number two, so let's say instead of going this way, the current is that way. So this is I. If I is that way, then it means the potential difference across the battery is equal to negative that. Okay. And then for a resistor, we have resistors going like that. This is negative. Let's say this is positive and negative. If you're going this way, then the potential drop across, potential drop across the resistor is equal to negative I R, where this is I, and the resistor is R. Okay. Like that. Okay. So this is the loop, the rule which I use, and then number four, apply the loop rule. Okay, and if you need a junction rule, then you apply it at that time. Okay, so let's look at a basic circuit and use these rules that we've talked about or we've mentioned. So we take a basic circuit. A circuit is basically a closed loop. So I'm going to take a battery like that, and then I'm going to run it through a resistor, roll it up this way. Okay, so I have negative, positive, and this is EMF. And so this is the resistor R. And I can assign, and I'll just follow what is in here. I'll assign the current direction I that way. Okay. So the potential drop in the loop must be 0. So the potential drop in the loop must be equal to 0. So it means that the sum of all potential drops must be 0. Okay, so I'll take the EMF. So if my current is going this way across the battery, then I have E, which is positive. Current is, this is positive, and that's negative, so the current is going that way. So minus I R should be equal to 0. Okay. So EMF here is equal to the potential drop across the battery. Okay. So we say that the potential drop across the battery minus I R is equal to 0. Okay, so the potential drop across the battery is equal to the current drop across the resistor. Like that. So let me see. So here, actually, let me redo this. Hold on a second. Let me redo this. Hold on. So we said the potential drop across the battery is equal to that. So if we continue along that, then we know that EMF is equal to IR. So the current I is equal to the EMF over R, okay, which is the potential drop of the battery. So now, let's do potential drop across the resistor is equal to the current times the resistance. So this will be written as current, which is E over R times resistor R, which is just equal to E. So it's just telling us the potential drop across the resistor is equal to the EMF of the battery. The EMF of the battery is just a potential drop across the battery. Okay.
What is that? ER? What's that branch? Is that
E what?
E over R, and then the next symbol after it?
E over R. I. This is I. Is that what you mean?
No, you got delta
Oh,
V
times.
Times.
Yeah. Yeah, this is multiplication.
It's canceling out the R.
Yeah, the R's cancel out. So the potential drop across the battery is equal to the potential drop across the resistor. Okay. So those are the only two elements there. Let's do an example of how this works so we can go on from that. So we start off with the battery like that. Let's say this is 1.5 volts and this is 20 ohms. So let's say the current is going in this direction. Okay, so by loop rule, by loop rule, we will say that the potential drop across the battery minus the current times the resistor should be equal to 0. Okay, so this is the E, this is R, of course, and that's I, so that should be equal to 0. And so the EMF is equal to I times R, or the potential drop. This E is just a potential drop. E is EMF. Actually, let me define it better. So that E is electromotive force, or EMF. Okay. So E is just the potential drop across the battery. So we can find the current here by taking E over R, which is just 1.5. Or let me write it this way. Potential of the battery divided by resistor, so it's going to be 1.5 over 20. Okay, so 1.5 over 20 is 0.075 amperes. Okay, so now the potential drop across the resistor is equal to this current times the resistance. So we just take the current, which is 0.075 amperes, multiply that by the 20 ohm resistance, and that gives us the potential drop across the resistor, which should be 1.5 volts. Okay. Any questions on that? So now there's another example that we can do. So we'll find the current in the circuit and the potential drops.
You mean voltage drop?
Sure, voltage drop. Voltage drop is the same as potential drop. Yeah. Maybe you're used to using the term voltage drop instead of potential drop, but it's the same thing. Okay. So we can assign certain values, of course. We can say R1 is equal to 5 ohms. R2, let's say, is equal to 3 ohms. E1 is 6 volts. E2, let's say, is 9 volts. Okay. So one of those batteries is going to be charging the other, basically, because we have two unequal batteries in the circuit. Let's assign a direction to the current flow. Let's say the current flow is this way. Okay. So in this circuit, we shall say by applying the rule, by applying loop rule, this is what we should have. So the elements of the circuit are E1. So if we are going this way, the current is going that way, then this is negative and that's positive. That's positive, that's negative, and we're going from positive to negative like that. So we're following the current. Okay. So by applying the loop rule, then we shall say E1 is positive minus I R1 minus E2 minus I R2 should be equal to 0. So the loop rule just tells us the potential across battery 1 minus potential across battery resistance R1 minus the potential across battery 2 minus the potential across resistor R2 should be equal to 0. That's all we are doing. Okay. So we need to find current. So we shall say E1 minus E2 is equal to, so let's do it this way first. E1 minus E2 minus I1 minus I R1 minus I R2 is equal to 0. So E1 minus E2 is equal to I R1 plus I R2. So E1 minus E2 is I R1 plus R2. So this allows us to find I to be equal to E1 minus E2 divided by R1 plus R2. So that gives us the current I in the circuit. So we can calculate I to be equal to E1. What was E1? 6 volts. Okay, minus E2 is 9 volts divided by R1. What is R1 and R2? Okay, thank you. So it's going to be minus 3 volts divided by 8 ohms. What is that given us?
4.875.
What?
4.875.
3 over 8?
I got 4.8.
That seems too high. This has to be a decimal. 3 over 8. What is 3 over 8?
0.33.
About 0.3.
3 divided by 8 has 0.375.
Okay, thank you. So about 0.375 amperes, negative 0.375. So now that we have current, the next thing we need to do, so anytime we are doing this circuit, what you need to keep in mind is we need to find the potential drop across each element, and then we need to find the current through each element. So once we have the current through the whole circuit, we can multiply now by the resistance in each element to find its potential drop. So now we can say that the potential drop across the resistor R1 is equal to the current times R1. So this is 0.375 multiplied by 5. So what is the potential drop across R1?
Negative 1.8.
Negative 1.8 volts. And what is it say? Is that right?
Negative 7.875.
1.875. And then the potential drop across R2 is I times R2, which is going to be equal to what? And R1 and potential drop across R1 is already negative, so we can remove the negative sign from there. It is also negative. Yeah. 1.125. Okay, thank you. So those are the potential drops across the two circuits. Okay. And the difference between, or the sum of those two should be 3 volts, which is the difference between the battery, the two batteries, 6 and 9 volts, if you look at it that way. 1.875 plus 1.125 should be 3 volts. Is that right? Yeah, so that's the difference between the two batteries, E1 and E2. Oh, sorry, yeah, that's the difference between the two. So we found a potential drop across each element. Okay. So we'll be doing this kind of exercise a little bit more as we go along. Okay. What is that? Why did I do what? Well, because the potential drops that we already defined are negative. So remember that the potential drop is already negative IR1. Potential drop is negative IR2.
Either way, interesting.
Yeah, so this is delta V is equal to negative IR1 for R1, which is what we put in the circuit when we did the calculation. And as I mentioned to you, remember that the negative sign only tells us that the direction we chose is opposite. So since we end up with a current which is negative, what that means is that the direction I chose is actually opposite to the true direction. So the current should actually be going this way instead of the way I chose it. That's why we had a negative sign.
Direction.
Yeah, it's just a direction of the current. It is not a vector. It's just a direction. It just tells me that I chose the opposite direction. If I had gone this way in the first place, then I would have ended up with a positive current. Then all these questions will be not necessary. Yeah. So those are the things we need to keep in mind. We'll do it more as we go along. So let's look next at 31.3. We'll come back to these circuits later on. So we're going to look at energy and power in the circuit. Energy and power. Okay, so in our circuit, we can say that the work done, so energy used is the same as work, which is the same as, so we'll say energy used is work done, and power, which is the rate of doing work. We'll use our basic definitions of energy and power as we go along. So we know that the power is equal to the rate of doing work. So this is the rate of energy use of work. So let me see. So in the circuit below, so I'll just use this circuit here. So this is current, this is E. So in this circuit here, we can say that the work done is equal to the charge times the potential. So U is equal to charge times the potential of the battery or the EMF like that. So the power dissipated in the battery is equal to the rate at which energy is used in the battery, which is U, which is just dBT times Q times E, like that. So we can say this power is equal to the current times the EMF or the potential drop across the battery. Remember that the QDT is current. Okay. So the unit of power is the watt. I think we've seen that before. Symbol is W, and the watt is one watt is 1 joule per second. And then let's see what else we do. So in our basic circuit that we have there, we know that the potential drop. So we say that we know already that the potential drop, so delta V of the battery is equal to the potential drop of the resistor. So that tells us that the power usage in the battery is equal to the power drop in the battery is equal to the power used in the resistor, like that. Okay. So whatever power is delivered by the battery goes through the resistor. So power in the resistor is equal to current times potential drop in the resistor. which is equal to current times I times R, which we can write as I squared R. So the power used in the resistor is I squared R. We can say that by Ohm's law, V equals IR. Therefore, we can say I is equal to V over R. So if you want to write it in a different form, then we can say the power used in the resistor or power dissipated in the resistor is equal to V over R squared times R. So it's going to be V squared over R. Okay, V squared over R. Then we use delta V just like we did for the resistor. So delta V, so it's delta V squared over R for the resistor. This is the power dissipated in the resistor. So it's the same as the power used in the battery also, because there's only that one component in there. If we have two components, the same current flows through them, but you have different power usages because you have different potential drops or different voltage drops. So they'll use different amounts of power. So let's look at series resistors next. So we can say that in a circuit where there are multiple resistors connected in series, we can analyze as follows. So let's say that we have a battery like that, and then we have several resistors like that. So we say I'm going to use E again. This is R1, R2, R3, and R4. So we take a current going this way, we call it I, and apply the loop rule again. So we'll say that by loop rule, then we say E minus I, R1, minus I, R2, minus I, R3, minus I, R4 should be equal to 0. Like that. And then we'll say that the EMF of the battery should just be equal to I, and then we'll have R1 plus R2 plus R3 plus R4. Okay. We already know that the EMF in the battery is just equal to the potential drop across the battery. Which can then be written as the current in the battery times a certain equivalent resistance going through the battery. So then we can replace EMF by I, R equivalent, and set this equal to I. And we have R1 plus R2 plus R3 plus R4 So if you cancel the R's, then you can say that the equivalent resistance in a circuit where there are 4 resistors in series is given by R1 plus R2 plus R3 plus R4. So resistors in series just add up as individual resistors. Okay. So we can say that for N resistors in a circuit, the equivalent resistance which is R equivalent is equal to the sum of all the resistors in the circuit. Just like that. So now that we know that, we can just redraw the equivalent circuit for the circuit that we have there, like that. So this is EMF again, and this is R equivalent. So once we know the equivalent resistance, we redraw the circuit that way. And we can say that the current through the circuit is just the EMF of the battery times R equivalent, just like that. Okay. So now when we know the current, we can then go and find the potential drop across each element in the circuit. We'll say now, let's find the voltage or potential drop up using potential. So let's call it that. So then we'll say that the potential drop across R1 is equal to I R1, like that. And so potential drop across R2 is equal to I R2. Potential drop across R3 I R3, and potential drop across R4 is equal to I R4. And the sum of all potential drops should be equal to E. Okay. Let's try one example to see how this works. So we'll draw a circuit like that. So let's say this is 1.5 volts. This is R1 equals 20 ohms, R2 equals 40 ohms, and R3, let's say, is 15 ohms. Let's make it 10 to give us a big difference, 10 ohms. Okay. So we choose an arbitrary current direction. Let's say the current is going that way. So we know that R equivalent for a circuit containing series resistors is just equal to R1 plus R2 plus R3. So R equivalent to be 20 ohms plus 40 ohms plus 10 ohms. So that will be equal to 70 ohms. Okay, so that's the equivalent resistance. So now our current I is equal to, actually let me do it this way so that you can see what I'm doing. So the equivalent circuit can now be drawn this way. So I have my E again, which is 1.5 volts. And then now I have R equivalent, which is equal to 70 ohms. And I know the current flowing through it is I. So now I can say I is equal to E over R equivalent, which can be written as 1.5 volts divided by 70 ohms. So that is the current flowing through the equivalent circuit. So the current through this circuit is going to be 0.02. Yeah. Tell me if this is not right. I think it's 0.02. Okay, thank you. 20 milliamps. So now, once we know the current, we can go back and find the potential drop across each element. Or potential drop across each resistor. Since they are all resistors, let's just say across each resistor. Okay, so potential drop across resistor 1 is equal to 0.02 times R1, which is 20 ohms. So this is equal to 0.4, thank you, 0.4. Potential drop across R2 is equal to 0.02, which is a current, multiplied by 40 ohms. So this is 0.8. And the potential drop across R3 is equal to 0.02 times 10 ohms, which is equal to 0.2 volts. Okay. So now we can now draw our circuit again. So we draw our circuit this way. So we said this was 1.5 volts. So the potential drop across R1 is 0.4 volts, R2 is 0.8 volts, and this is 0.2 volts. So we know that since the loop rule tells us the sum of all potential drop is equal to 0, then we can say that the EMF should be equal to delta V1 plus delta V2 plus potential drop across 3, which is 0.4 plus 0.8 plus 0.2. Here we have 1.4 volts. Okay. So that tells me that we have some decimals missing from the current. Or we just, so, what is it? I think it's
0.0217.
Yeah, 0.0214.
214. Okay. Yeah, 0.0214. So if you put that in correctly, let's use that and we'll get the exact number. But let's do it this way. I'm going to leave this out and I'll just say that, so I'll leave that the way I had it. And what I'll do here is I'll say that the actual current is I equals 0.0214 volts.
It ends up being like 1.498.
Yeah, it should be very close to that. So if we don't round it up, it should be exact. So then we shall say that delta V R1 is 0.0214 volts times 20 ohms. That's 0.0214 amps, not volts, amps, times 20 ohms. Then we have delta V R2 0.0214 amps, that's 40 ohms. Delta V R3 equals 0.0214 amps times 10 ohms. So give me those numbers so that we can add it up. 0.428. Okay.
0.856.
Okay.
0.214.
Okay. So then you add all this up and you should get something like what, you said 1.49, what was it? 1.48?
498, yeah.
Yeah. Which is approximately 1.5 volts. Okay, so that's how we should do it, or that's what we should be getting. Should be pretty close to the exact number.
So in dealing with currents, then first the second order.
Yes, it was my fault to just make it 0.02. I was trying to make it simple, but in this case, to illustrate the point, I should have left all the decimals in. You know, just to point out to you that it is exact. If the EMF is 1.5 volts, then the potential drop across each element, if you add them all up, you should have the same, 1.5. Yeah. Let's do an exercise. Okay, so try that and let's see what you get. Once you complete it, you'll be able to check that the sum of all potentials is equal, should be equal to 1.5. So if you are close to 1.5 volts, then you know you've done it right. So what is the equivalent resistance?
115.
115. Okay, 115 volts. So the current through that circuit can be written as the EMF over equivalent. So we have 1.5 divided by 115.
It's 115 ohms, right? Yeah.
Yes, ohms, not yeah, I wrote ohms down there, but writing volts up here. 1.5 ohms. So the current is equal to what?
0.01304.
Okay.
0.014.
0.01304 amperes. Okay. 0.01304. Okay. So then we can say that the potential drop across 1 is 0.01304 times 30 ohms. Then you do potential drop across 2. What was that? Let's see. 40. So what give me the numbers for the first one?
0.391304.
Second one,
0.26086.
third,
0.521739.
okay,
0.195652. 0.043.
So when you add it all up, what does that give you?
1.49996.
Okay. You see that the more decimals, the more points you have behind the decimal points, the closer it gets to 1.5. So it should be pretty accurate. 1.49. So when you do it is when you check it, and that tells you you've done it right. So you can always check your work. If you end up to be less, actually not equal to the 1.5 volt of the battery, or whatever the battery is, if you are not getting that number, it means you made a mistake somewhere. But this is pretty straightforward, so you shouldn't have any errors. Let's move on to ammeters on this section. So we are putting ammeters here because ammeters are typically connected or always connected in series with the element that you want to measure the current through. So we'll do that here because we are looking at series resistors. So let's say we have our circuit like that. We have a resistor in here and we want to find the current through it. So we connect an ammeter in series with that. So this is the resistor and this is the ammeter. The ammeter itself should have some internal resistance or have some resistance. Let's call it lowercase r. Okay. So we can apply the loop rule. So let's say the current I is the current we are trying to measure. So if you recall, we always connected the ammeter in series. So by using the loop rule, the EMF minus I R minus I lowercase r should be equal to 0. So we can say that EMF should be equal to I, and have R plus lowercase r equals 0. Okay. So then the current we are trying to measure can be found by E over R plus lowercase r. So what this tells us is that we want to have an ammeter which doesn't influence the current that we are measuring. Because if we have an ammeter with a resistance R, let's say if R is equal to the resistance of the element that we are interested in, that is basically going to split the current up. Okay, so let's look at what happens when you have that. Let's say that suppose R, which is the resistance of ammeter, is equal to R, which is the resistance of the element whose current we are trying to measure. Then we can say the current is going to be equal to EMF over R plus R, which is going to be the EMF over 2R. So I is going to be, let's see, so we can say that I would be equal to half E over R, like that. Okay, so basically, if we have a resistance in the ammeter which is as large as the resistance of the element we are interested in, that basically splits the current. So the current is not measured accurately. So ideally, we can say that so we see that if the ammeter resistance is anything other than 0, the current measured will be less than the true current in R. Okay, so this is a feature of ammeters, is that they have an internal resistance which is close to 0. So R is approaching 0 or R is equal to 0. Okay, for an ammeter. So that the current measured is just the current through R, the element we are interested in. The ammeter itself does not have any potential drop across it because the internal resistance is 0. Okay. Questions on that? All right, very good. So we can go to real batteries and then we'll stop before we get to parallel resistors. We'll do that. Actually, we can wait and do parallel resistors and real batteries when we come on Thursday. Okay. So let's stop here. When we come back on Thursday, we shall start with real batteries and then we'll do parallel resistors and voltmeters and go on from there. Okay. Any questions? Okay. So we'll save this.
Oh,